just going to move this little window out of the way here so we can, All right. So good morning, everybody. It's really nice to be here and for all of you to be here. And it's been a lot of work on Amy Herfort's part to get you all here. So I'm glad that we're all here and it's a wonderful spot. And I feel like it's been a very long time since I've been at a summer school. When was the last summer school that has been held? Like pre-pandemic, like maybe 2018 or 2017, I think. It's been quite a long time. This morning, we're going to talk about simple models. And for, there are a few Guelph students, actually, we're missing a few Guelph students. For Guelph students who took mathematical modeling with me in the winter, some of these slides, first thing this morning, are going to look a little familiar. But it's good review. It's good review for you. Because really what we need to start to understand is just the biology of setting up models. So thinking about host pathogen relationships, thinking about population dynamics, thinking about how we take all of that biology and translate it into a mathematical model that we can then use to try to understand what's happening with the system. And so my name's Amy Greer. I'm going to be around for the summer school. I'm at the University of Guelph. I've been there for about 10 years at this point. And before I was at Guelph, I was at the School of Public Health at U of T and at the Public Health Agency of Canada. So have worked as both kind of an academic scientist, but also in government. And so when I think about modeling, I really think about it predominantly initially from kind of the biological application perspective. So we're going to start with thinking through some of that and figuring out how to get on the same page so that moving forward over the next 10 days, everybody's kind of up to speed. So, we're going to talk about infectious disease modeling, and we're going to talk about diseases that are caused by lots and lots of different types of organisms. That could be viruses, bacteria, parasites, protozoa, or their biological products. So some pathogens cause illness, not by the pathogen itself, but because the pathogen creates toxins that then create illness in the host species. And, one of the most important and interesting things I would argue about infectious diseases that makes them a little bit different is that aspect of communicability, because a case is also a risk factor for everybody else. And cases can sometimes be unrecognized. And I think we have, come to a point in time in the pandemic where many individuals, even if you didn't really know much about infectious disease biology before, have really understood that there are a lot of different pieces of these puzzles that feed together. And so when we say cases may be unrecognized, one of the real challenges with communicability is for pathogens that are able to transmit before the individual knows that they're ill. And so what happens in the models that we're going to create is that communicability manifests as positive feedback. So the more cases you have, the more cases you get, essentially. Infectious diseases are also really interesting for us to think about because there's just such a wide variety of host pathogen relationships, and they can range from very simplistic relationships all the way to, very complex systems that have lots of different hosts that incorporate the environment, that have lots of different factors that contribute to the way they get introduced and spread in populations. They have, incredible capacity for change, and we see continued emergence of new pathogens, which we're going to talk about next when we talk about spillover. And really what all of this means is that when we think about interventions, which is something that we're going to talk about again next week, kind of more intensely, is that when we attempt to intervene in these systems, control really depends on the herd, not just on individuals. And so when we talk about herd, I mean the population. So typically we can classify infectious diseases in different ways. We can talk about them based on clinical syndrome, so diarrheal diseases, respiratory diseases, central nervous system diseases. So based on kind of the clinical constellation of symptoms, we can class them based on the microbiology, which is kind of the more typical way that you might think about it. We can also class them based on the mode of transmission. And this is really important to understand the mode of transmission because, again, when we're trying to convert the biology into simple mathematical equations, we really have to think about how does this pathogen transmit, because we have to make sure that we are representing the mode of transmission in the model appropriately. So that could be through direct contact, it could be a food or waterborne pathogen, it could be an airborne pathogen, vector-borne, so a pathogen that's transmitted by ticks or mosquitoes. And we also need to think about whether or not there are reservoirs for the pathogen. And again, when we talk about spillover, this is going to be something that comes up, which is that for some host pathogen systems, there are places where the pathogen can be that we also really need to think about. So for instance, you might have a pathogen that's transmitted person to person, but perhaps the pathogen is also found in a population of animals, or perhaps it is found in the soil. And so we have to think about not only your risk of contact with individuals, but also your risk of coming in contact with contaminated soil. We also have to think about the way in which transmission occurs, because we have to think about what we call horizontal transmission, so transmission from one to the next, versus vertical transmission. And so vertical transmission is when the mother transmits the pathogen to the infant, typically in utero, and then the individual is born with an infection, which we see with some STIs, for instance, and some other infectious diseases. So again, all of these pieces of the biology we really need to be thinking about as we start thinking about how we structure those very simple starting models. And it's also really important, as somebody who's an infectious disease epidemiologist, for us to think about the terminology, because a lot of the terminology when we read papers, for instance, because when we develop models, and often we'll go to the literature to say, okay, let's find some parameter values that we might want to put into these models. It's important to kind of recognize that the terminology is important. And sometimes different epidemiologists use different words for the same terminology or slightly different variations. So sometimes you do have to read quite closely to figure out what it is that they're trying to tell you. So when we talk about infectivity, what we're talking about is the capacity of the organism to infect individuals that are exposed to disease. So we typically call this the ID50. And really all it means is how much infectious dose, like how much pathogen do you need to come in contact with to actually become infected with the infection. And so for instance, Shigella is a bacterial pathogen. You get infected if you could get about 200 organisms, whereas for Salmonella, you need to have about 200,000 organisms. So there's a quantity, a magnitude of difference here. Does anybody know about norovirus? Has anybody heard of norovirus? Yes, norovirus is like the horrific, what we call the winter vomiting and diarrhea illness. And so norovirus is a very acute infection, but you only need one viral particle to contract norovirus. So the infectious dose of norovirus is very, very small, which is why you see incredibly explosive outbreaks when you see outbreaks of norovirus, especially in congregate settings. Pathogenicity is the word we use to talk about the likelihood that an infected individual will become clinically ill. So, sometimes people become infected with a pathogen and they actually don't become unwell, right? Sometimes they can have an infection that's very mild. And it's important to think about this because, you will feel physically unwell if you're infected with the cold or if you're infected with SARS, but they have high pathogenicity but different virulence. And so we're going to talk a little bit about that as well. So really what we're talking about here is the likelihood of severe illness among those infected. And so things like SARS, the original, now I have to call it SARS, the original SARS, SARS-CoV-1, avian influenza, so H5N1, very virulent with a case fatality rate of about 75% in 2004, and norovirus infections, right? High infectivity, high pathogenicity, because an asymptomatic norovirus infection is pretty much unheard of, but the case fatality rate is low in otherwise healthy adults. So again, all of these things are pieces of the puzzle that we have to think about when we're thinking about host pathogen systems. We also have to think about the immune system, right? So some infections result in long-lasting immunity. So the host is not infected again. So you become infected, you mount an immune response, and then for some pathogens, you have lasting immunity for the rest of your life. So we have lots of pathogens that have high immunogenicity, but then we also have pathogens with low immunogenicity. And so these are things like gonorrhea or chlamydia, where individuals can become repeatedly infected because they do not mount an immune response that lasts. So that means their immunity wanes over time. So again, those are things we have to think about when we start structuring simple models, because it allows us to think about how the population behaves. If individuals don't become immune, if they kind of lose their immunity over time, that means they become resusceptible to infection. And so we have to incorporate that into the structure of the model, or else we will not have a model that gives us an outcome that's in line with what we really observe. We also use terms like the attack rate or the clinical attack rate to describe, the number of individuals infected out of the population as a whole. Clinical attack rate is a little bit different because this is obviously individuals who have developed clinical illness, not just the group of people who have all become infected, because we know that for many infections, some people will have an asymptomatic infection. So again, these are important for us to think about. If we're thinking about data sets, can anybody think about why this is important when we think about data that we might use for infectious disease modeling? Clinical versus just an attack rate. Where do you think, so the individuals who we would consider to be infected in that clinical attack rate group, if we were calculating it out, do we see them anywhere? Like, where do we find those individuals? Hospitalization, for instance. So that's a really good example, right? So if we're thinking about this, we have to always remember that we have something called like an epidemiological iceberg, essentially, which is that at the very top of the tip, those are the individuals that we see. Those are the people who get counted in the surveillance data. So if we're thinking about human infectious diseases, we have publicly available data that you can go online and say, how many people have been hospitalized each week in Canada for a specific infection, for instance, for notifiable diseases. But we have to always remember that the individuals who show up in those data sets are really only a subset, right? Especially for pathogens like food or waterborne pathogens, where we know there is very significant underreporting, right? Norovirus is not reportable, so you won't find, a clinical attack rate anywhere publicly. But we also know that for many other gastrointestinal illnesses that are reportable illnesses, most people don't actually go to the hospital. They don't go see their physician as a result of their infection. They kind of just wait it out, right? People who get salmonella, food poisoning, they wait it out. And so we have to always remember that these are a little bit different, right? Because what we see in the data is the tip of the iceberg. Those are the reported cases. And underneath the water, there's typically this much larger group of individuals who we don't see. So one of the things that we talk a lot about in terms of epidemiological definitions is the reproductive number. So how many people have heard of the reproductive number? Probably most of you, Jane's like. So this is the number of secondary infections produced by each primary infectious individual in a fully susceptible population. And this is really important to think about, because we also have to, when we start thinking about setting up simple models, we have to think about what our population looks like in terms of their immune status. And the reason this is important is because if we think about something like an emerging infectious disease, where it's an infection that's come into a population, whether it's an animal population or a human population, if the infection emerges and is new, what does that mean about the susceptibility of the population it's coming into? If it's a new pathogen that's never been seen before, or a variation. Very high. Very high, right? So the susceptibility in the population is high. And that means that, you know, in the situation where you have the introduction of a new pathogen into a fully susceptible population, the epidemic growth potential that exists in that sort of a population is very different than in a population where, for instance, there has been some historical, you know, infection in the population, so that not everybody is susceptible. And we're going to learn a little bit about that as we go. So really, this allows us to kind of have this threshold, which says that, you know, when the R naught is greater than 1, that's when you're going to see epidemic growth. If the R is equal to 1, then the disease will kind of just bump along at a low-ish level. It doesn't have to necessarily be at a low level, but it bumps along in what we call an endemic state. And if it's below 1, eventually over time, we would hope that maybe it would go away. So to give you an example, here we have the initial phase. So this is our initial infected individual. And if the R naught is 3, what we mean to say here is that one infectious case generates 3 new cases before the end of their infection. And then each of those individuals goes on to generate 3 new cases, right? So this is really how we get that growth phase. We start with 1 and we end up with many cases over a period of time. Whereas if the R is equal to 1, for instance, we might have some immunity in the population whereby this case only generates 1 new case and these individuals do not become infected, and then they generate 1 new case on top of that. And so we don't see growth, we just kind of see replacement, right? You start with 1 and then you get a new infection and then you get a new infection. So it's not growing, we don't have that like increasing trajectory, but it kind of just stays at a steady level. The important thing to remember, though, is that R naught is kind of an oversimplification, right? Because we talk about it like as if it's like a written in stone sort of value. And the important thing for us to remember is that it's really the mean of a distribution in a lot of ways, right? Because not every single person is going to infect the exact number of individuals that we calculate if we figure out what the R naught value is. And this is a really good example which talks about heterogeneity of transmission to give you a sense of how variable this can be, right? So this is an example of an early transmission chain of SARS-CoV-2 in Singapore, where we can see that individuals, these 2 individuals came to attend a church service, actually. So there was a lot of contact with a bunch of people at this event, and one of these individuals was infected. And, you know, they went on to have a bunch of contacts and they generated, you know, 1, 2, 3, 4, 5. So this chain generated 5 new infections. But then this A2 individual down here, they went about their business and they generated all of these new infections. And then this individual F1, they generated this big group of infections, right? So it's important to remember that although we use the number, there's a lot of variability. There's heterogeneity for many, many different reasons, right? Can anybody think about reasons why you might see heterogeneity in these sorts of dynamics? Like what's happening here? What are some of the components that play into that? We think about SARS-CoV-2, if we think about this transmission chain, like how is transmission happening here? Why do some people transmit a lot and some people not transmit very much at all? Yeah.
Like where they're living, if they're densely populated near their house or going out a lot.
For sure, right? Contacts. The amount of contact you have with people plays a big role. If it's a pathogen where you have to have, close proximity contact with the person, then contact. Some individuals have a lot of contact. You might have a job, for instance, where you have a lot of contact. You might have a job where you work in your office by yourself with the door closed all day long and have far less opportunity to contact individuals. We know there are lots of kind of other components to that, right? Which is, if you're sick, hopefully you would stay home, and that artificially changes your contact, right? But there are lots of different circumstances that play into this heterogeneity, and we're going to talk about heterogeneity kind of across two different sections later on. So we have this heterogeneity among individual behaviors and individual infectiousness, right? Some individuals might be really super infectious and other individuals perhaps less so. We know, for instance, with SARS-CoV-2 vaccines, for instance, vaccinated individuals seem to shed less virus than unvaccinated individuals, which means that infectiousness also likely plays an important role in some of this heterogeneity. So we have to think about the fact that R0 can really be thought of as the mean of a distribution, right? So again, this is from an estimate from SARS in Singapore, where the average value was somewhere around here, but there was this very long tail, and we see that with many different types of infections, where we have this average, but it has a very long tail. And we talked a little bit about population susceptibility, right? And how the role that plays when we think about structuring some of these models. And so for perfectly immunizing or sterilizing infections, so we call a sterilizing infection an infection that when you become infected, you then are not able to become reinfected, right? So we consider that to be a sterilizing infection. In a homogeneously mixing population, this is something we're also going to talk a lot about, right? There are some assumptions in the initial models we're going to think about where we kind of assume you have a bunch of individuals and they're just homogeneously mixed, right? Everybody has an equal chance of coming in contact with everybody else. And that really is not the way the world works, right? And so a lot of this assumes homogeneous mixing. And again, when we talk about heterogeneity, we're going to take it a step further and talk about how we can structure models in a way that builds in some of that more realistic heterogeneity, especially in the way individuals come in contact with each other. So again, when we think about wildlife diseases, this is a really important one. And I'm at the vet school, so I worked in public health, so I use a lot of human infection examples, but we also work on a lot of animal-related pathogens. So again, this is really important, right? Because for animals, we don't necessarily know everything that they're doing, right? And so when we talk about animal populations, oftentimes we talk more about density, right? The density of the host population, because it's kind of like a surrogate for contact. We assume that, if the population of interest is very dense, then they have much more contact with one another. But we see the same relationship with that reproductive number. So the important thing about R0 is there's this really important relationship where we have a threshold for what we call vaccine-induced herd immunity. And all of these things we're going to talk about a lot more in detail. But the important and really super interesting relationship that exists here is that if we know the basic reproduction number of a pathogen, we can figure out how much vaccination would you need in your host population to drop that reproductive number below 1, right? So when we think about disease control, our goal, if we are working as epidemiologists or working in public health, if the reproductive number is up here and we're seeing a lot of transmission, our goal is to act in a way that helps to suppress the reproductive number. We want to do things that will allow it to drop below 1, which will allow us to get better control. And so we have this mathematical relationship between the reproductive number and the critical proportion to vaccinate. And so based on this very simple little equation, we can say, okay, well, you know, if we have rubella, which is a pathogen that has a reproductive number of about 6, we can find out that if we plug those values in here, we need to have about 80% vaccine coverage in the host population to be able to prevent outbreaks. Now, measles, for instance, has a reproductive number that's much larger than rubella. So as the reproductive number goes up, we have to have even higher vaccine coverage in the population to maintain that suppression of the disease. Can anybody think about why, like, what's happening with measles vaccine right now? Because what this tells us is that measles vaccine coverage needs to be very high to suppress. Does anybody know anything about measles vaccine coverage more recently? It's starting to go down. Measles vaccine coverage in many parts of the world have gone down quite a lot. It's patchy. So what I'll say is that measles vaccine coverage is patchy, which again, when we talk about heterogeneity, is something that we want to think about. So for instance, you know, at a population level, measles vaccine coverage in Canada is still quite high. But for instance, if you go to California, they have many measles outbreaks every year. And they're typically associated with school outbreaks where you have kind of specific locations where vaccine coverage is very low. So again, you know, there's this really interesting relationship where we can learn about what we need to do to intervene on the vaccine side in terms of population level immunity and the reproductive number. So the higher the reproductive number, the more vaccine coverage we need in the population. Can anybody think about another simple thing? So this kind of overlooks one important thing. What does this assume about the vaccine itself, right? Yep.
That you only need one shot to be immune forever.
Well, it possibly. It assumes something else, though, also. Yep.
It's 100% effective.
It assumes it's 100% effective, right? So that is an oversimplification in a lot of ways, right? Because we know that no vaccine, you know, some vaccines are very good. The measles vaccine is very, very good. So this is probably about as close as you're going to get to a really good sterilizing vaccine. But for many vaccines, it won't work perfectly in every single individual, right? So that's something we need to take into consideration. So, you know, the important thing about all of these disease dynamics is that to understand disease dynamics, that basic understanding helps to also inform the scientific basis for interventions. And so control measures, anything we do to act on the system to try to control the transmission of the disease, they operate typically by trying to first reduce transmission. And so this is like the first kind of compartment model we're going to see here, where we have, let's imagine we have a group of individuals or a population, and we're going to assume that the population is in one of 3 mutually exclusive health states. So if we have, you know, 100,000 people in this population, we have a susceptible compartment, an infected compartment, and a recovered compartment. Individuals can only be in one of those compartments at each time. So they are mutually exclusive. You can't be in more than one compartment. When we think about the reproductive number, how do we actually get that, right? What feeds into the reproductive number? We typically think about it as the contact rate times the probability of transmission given a contact times the duration of infectiousness. And that duration piece is important, right? Because if you're infectious for only 1 day, your capacity to create new infections is going to be quite different than if you're infectious for 14 days, or if you're infectious for, you know, 20 years, for instance, if you have, you know, undiagnosed tuberculosis or undiagnosed HIV. So infections that have a longer period of infectiousness are going to be quite different than an infection where the person's only infectious for 1 or 2 days. So we have to also consider the duration of infectiousness. And oftentimes you'll see that C and P kind of pushed together and called beta. So if we have this R naught, and we have these three different kind of parameters that contribute to it, why can't we just estimate it based on this relationship, right? So, you have this new outbreak and you think to yourself, oh, like I need to calculate R naught. But the trick is that for many diseases, figuring out what the contact rate is really difficult, right? Like what is a contact, for instance, right? That's different for a respiratory infection versus an STI versus a vector-borne disease. We have to think about what the contact actually entails, and then how do we parameterize that sort of contact, right? So we need to think about all of these things when we start putting together models. So these are some estimates of R naught, just to kind of give you a sense of the fact that they range, right? Like H1N1, so pandemic influenza H1N1 in 2009, the reproductive number was very low compared to these ones that are on here, right? The reproductive number was about 1.3. So it doesn't take much above 1 to really still cause a lot of infections. So, when we're talking about measles with a reproductive number of 10 to 20, that's very dramatically different. But that doesn't mean that, when you get close to 1, that means that, nothing really happens. Because once you cross that threshold of 1, you are going to see increasing cases. So R naught really tells us a few things about a disease. It tells us about the index of epidemic potential. There's this relationship with the critical fraction to vaccinate, to eliminate a disease. It tells us something about the initial slope of the epidemic curve. So, is it going to take off and go up very sharply, or is it going to take off and increase more gradually? And there's also a relationship with the final size of an epidemic that we'll talk about. But the other important thing here for us to think about is also there's a time component, right? And we talked about duration of infectiousness as an important time component, but we also have to think about the fact that there's a natural history to all infections that we have to consider in simple models. So the incubation period is the time from infection until the individual becomes symptomatic, right? So the time of infection is typically an unobservable entity, right? Like we can't pinpoint exactly when an individual was necessarily infected. That time from infection until you become symptomatic. This is important because if we know something about the incubation period, it can allow us to use that as a basis for very simple infection control measures such as quarantine. If we can identify infectious individuals with onset of symptoms, then they're already disconnected from the population, right? So if we know something about how long it takes for individuals to become symptomatic, then we can understand how we can adjust some of the timing of public health interventions. The latent period is the time from infection until you're actually infectious. And this is important because you could have an infectious pre-symptomatic period, right? So that means that you have your infection event happen, which is unobserved. So you don't really know when you were infected exactly, but you may become infectious before you're symptomatic. And we talked about that. So that makes control of a pathogen very difficult. If people can transmit before they have symptoms or before they know that they are unwell, that makes it really hard, right? If individuals become symptomatic at the same time as they become infectious, then stay home when you're sick works really well, much better than if you're infectious before you're symptomatic. So it's really difficult to institute control measures in the absence of symptoms. So again, all of these timing aspects are important when we think about structuring simple models. So the incubation period for some pathogens can be very prolonged. Or for some pathogens, the entire duration of infection may be asymptomatic. Some individuals with infections like hepatitis C may experience asymptomatic infection for their entire course of infection. it's estimated that about 40% of influenza cases are asymptomatic, right? So this is also important to really think about the biology of the pathogen you're modeling so that you make sure that you get the model set up with the appropriate biology. And we also know that there can be carriers where people maybe have a brief period of symptoms that's then followed by kind of a prolonged asymptomatic period. And so typhoid is an example of this, where individuals can be symptomatic for a short period of time, but then they're still infectious but asymptomatic afterwards, which is kind of the flip. So this is kind of how we would think about the natural history of a pathogen or a disease. So we have a latent period, we have an incubation period, we have an infective period. And so really what we need, if we want to think about, data for setting up some of these simple models, is that, we need information on both case counts and some sort of estimate of the time between generations of cases. And there are different ways to do this. So the rate of growth of an epidemic is a function of both the reproductive number and the time interval between successive generations of cases. Yep, sorry.
Please, I have a question about the incubation period and does it depend on the.
So that's a good question. So if we go back here, so you're talking about the latent period versus the incubation period, is that what you mean? So typically these are pathogen specific at a population level, but certainly there's going to be individual level variability, you're right. So, we might say, well, the average latent period is 3 days, but, you might have a bit of variability on either side, depending on each individual, right? So it is pathogen specific, but there will be a little bit of variation, certainly, depending on individuals. Yeah.
Yeah, so from this chart, the incubation period, there's a time where the incubation period, the individual will be infectious. Yeah, so I'm trying to understand the difference between latent period and incubation period. I mean, I had always thought it will mean the same, like the time where the individual is not infectious. But from this, I could see that at some point in the incubation period, the individual will become infectious to others that come in contact with.
So it depends on the pathogen, right? So this is typically how we would think about it as epidemiologists, but you're right, is that for some pathogens, this is kind of the same thing, right? So it depends on the pathogen. So you're exactly right. Not every pathogen has a biology where you're infectious before symptom onset. So that is true. So this is perhaps somewhat misleading because I broke it down this way to give you all of the different possibilities, but you're exactly right, is that for some pathogens, this onset of symptoms happens at the same time as when you become infectious to others. James.
Yeah, so would something like the term asymptomatic period be equivalent to incubation, or does asymptomatic have different baggage?
Yeah, yeah, I mean, technically as an epidemiologist, we would call that asymptomatic, right? Because you're in a period before your onset of symptoms. So in this case, we would say, if this was the actual breakdown, we would say this was the asymptomatic period, and then this is the symptomatic period.
Okay, so that does get used.
It does get used, for sure. Yeah.
From like a virology standpoint, we like to think about incubation versus asymptomatic based on the viral load in the individual instead, if that makes sense.
Yeah, that's a really good example, right? Because this, again, talking about variability, is that every discipline, right, considers things a little bit differently. So you're right, if you're a virologist and you're interested in viral load, and we say, well, you only become infectious after you've passed some threshold of viral load, that's going to be different than somebody like me who's an epidemiologist who sees it really at an individual person level. I don't know what their viral load is. I just wait until they test positive. And to me, it doesn't really matter like what their viral load is. for my purpose. So you're exactly right. Again, based on your discipline, if you're interested in, viral load, this is going to look a little bit different, because you might say, okay, well, you have infection and then your viral load is increasing. Maybe you become infectious to others at some point where your viral load passes some threshold, and then you don't develop symptoms until your viral load hits some next threshold. So the threshold is defined based on a more quantifiable entity instead of kind of an observable individual entity. It's observable if you have like a qPCR machine, I guess, but maybe not otherwise. So, so what I wanted to kind of talk about really was that we use this common heuristic, which is that the serial interval is latency plus half the duration of infectiousness. Again, it's an oversimplification and it assumes transmission at the midpoint, but I want to show you an example looking at measles and TB, assuming they both have an R0 of about 12. So let's think about this individual who becomes a case. So here's case number 1. Case number 1 goes through their latent period, and then they enter an infectious period. And then if we assume that they transmit their infection at the midpoint, which is an oversimplification, but we're just going to say they transmit at the midpoint to case number 2. And then case number 2 starts their latent period and goes through their infectious period. Then we would say this is the serial interval. Now, the important thing is that, so really it's the time between case 1, when we observe case 1, and the time at which we observe case 2. Now, the interesting thing here, if we think about time, is that for measles, this whole thing happens in the span of days, right? Whereas if we're talking about HIV or tuberculosis, sorry, this whole thing happens on the scale of years potentially, right? It might take a few days to generate case 2 if you have measles, but if we were talking about a TB infection, it might be several years of time between infection in case 1 and the infection in case 2. So really what we can say is that for a given generation and a given R0 of, let's use the example 3, we can figure out the number of incident infections in the generation. So if we have generation 0, we have 1 case, so we start with 1. Then in the next generation, so we have 1 case, which leads to 3 cases, right? And then we start with the cases. In generation 2, we have 3 cases, 1, 2, 3, and at the end, we have 9. So again, there's a relationship where we can calculate R0 to the T. So let's talk a little bit about how we take all of this kind of biology and public health information, and then we put it into a model. So, mathematical models are conceptual tools that explain how an object or system of objects will behave, right? It's not a perfect representation of the system, but it's really a pretty good proxy for what we believe is happening with the biology and with, for instance, the public health interventions. Some models are very simple, some models are highly complex, and really anywhere in between. And a lot of the decisions about how complicated the model is going to be driven by lots of different things, right? First, how long you have to generate the model, right? Generating models during a public health emergency is very different than generating models as an academic, where you have a much longer timeline to be able to do the work. It's very often going to be generated by the data you have available to you. For many pathogens, there's not a lot of good information necessarily for all of the different parameters you might want to put in your model. So you have to think about, where would I get data from? Can I go to the peer-reviewed literature? Do I need to collect some of that data myself? There are lots of different questions you would ask yourself about structuring your models. All models make simplifying assumptions, right? In a lot of cases, that individual level heterogeneity, unless we're developing an individual model, we kind of gloss over a lot of that, right? We tend to use averages, we use common behaviors, and we don't really consider, unless we're building like an agent-based model where we want to look at individuals per se, we kind of make a lot of simplifying assumptions. But the goal really is to capture the essential features. And one of the things that's important, and I say this as an epidemiologist who frequently talks to epidemiologists who are really used to statistical models, right, is that it's really important to understand that I'm not talking about like regression models. Statistical models, as epidemiologists, we use them to describe associations between variables. And statistical models are amazing for deriving parameter estimates from empirical data. It's great to have statistical collaborators, people who collect data, people who can understand data sets so that we can use them in mathematical models. But really, they're quite fundamentally different. The mathematical models really propose the causal pathways, describe the mechanisms that we believe link those different things, right? Exposures and interventions, infection, disease, and we can use them to make projections. So I would argue that they're linked, but they're importantly distinct, right? So, the statistical models are kind of the data piece that feed into the models, and then we can use models and say, hey, there are some gaps here. There's a lot of uncertainty around these parameter values, and we don't really know what the values should be. So it's really nice to be able to go back to your colleagues who collect data or who are statisticians to try to get better estimates so that it's really an iterative process. So really what we want to do is we want to think about the process as formulating a problem or objectives, developing a conceptual model or compartment diagram, then translating that into some equations, and then getting it into some sort of software that we're going to use to solve those equations, which in the case of this will be R. So really what we're doing is we're abstracting a very complex system, right? We're taking this, which is very complicated, and we're abstracting it down to only its most important parts based on what the purpose of our model is, based on the different components we want to include. And then we're going to run the model over there, and then we're going to interpret those results back to kind of the real world, taking into consideration the assumptions we've built into the model, taking into consideration the limitations of the model, and whether we are able to validate those results in the real world. There are certainly trade-offs between things like accuracy and transparency and flexibility, which I won't go into, but are in the notes here that you can look at. And I would say that, a good model is suited to its purpose, right? Is that we really have to have that accurate balance of accuracy, transparency, and flexibility, and that's going to depend on the purpose of your model. Ultimately, your model has to be parameterizable, right? You have to be able to have data to put into the model. Otherwise, it's not going to be a very useful model, but it is going to be highly context dependent. So, to kind of take us into the last little section here before coffee, the goal here is to walk through kind of how you take this biology and put it into a model. So you're going to first think about your host population of interest, right? For some of you, this might be a human population. For people who are working on, veterinary diseases or wildlife diseases, your host population might have nothing to do with people. It might be a group of cows, it might be a group of foxes, it might be a group of whatever your population of interest is. And then you need to define the states of individuals that will be in the model or the compartments. So, we talked about how you have this mutually exclusive health states. And again, this is kind of the simple version, right? SIR. But there are lots of variations on this, right? We've talked about all of the complicated biology around latency, for instance, right? So your biology might tell you, hey, you know, this doesn't quite get it right because we need another compartment in here, right? Maybe we need an exposed compartment. Maybe we need a compartment that's like, maybe we need an exposed compartment and an asymptomatic compartment. Maybe we need, so you have to really think about, again, what's your question? What's your host population of interest? And then you need to figure out what states do you need in the model based on your question for your pathogen of interest. And then you need to think about what are the transitions in and out of the states, right? Again, translating the biology onto these compartments. So who can tell me what is inherent to the biology? So I haven't told you anything about the biology of this pathogen, but does this compartment model with the arrows tell you something about the biology of this pathogen? Yep.
Once you're infected, you can become susceptible to the disease again.
You can become susceptible again, right? So in this case, the transitions very clearly tell us that you become infected, then you do recover from your infection. And if you're in here, you would be considered immune to reinfection. But there is this transition where at some point in time, individuals are coming back into the susceptible compartment. So this would be, you know, a model we might use for something like chlamydia, where individuals become resusceptible over time. It wouldn't be a good model for something like measles, where we know that that doesn't happen. This arrow here is not something that we would see in a model that generates, you know, long-term, lifelong immunity. So again, we have to think about the transitions, right? So we're going to come up with our compartments. We're going to put the transitions in based on the biology. And then we need to think about, you know, how does infection incidence depend on exposure to infectious, I say people here, it doesn't have to be people. So we have to kind of think about, this is the transmission part, right? This is the part of the model where susceptible individuals essentially become converted into infected individuals. So we have to think about, what do we put in there, right? What is that, that transition? What does that force of infection look like? And so here, what we're saying is the force of infection that's going to happen there is going to depend on the number of infected individuals in your population, right? So this is that communicability, that's that positive feedback. The more cases you have, the higher the force of infection is going to become. So if we think about a simple model, and so how many of you are math students? Some of you, but not everybody. Julian's like, no, Julian's laughing. How many of you are not math students? So there's, okay, so I mean, there are quite a few. Okay, so like for some of you, if you've taken, you know, introductory modeling already, this is probably pretty simple. But so, you know, when I talk to biology students or when I talk to epidemiology students, the way I explain this idea of having individuals move between the compartments is I want you to think about a bathtub, right? So if you think about a bathtub, you can have an inflow, you can turn the taps on and the water will come into the bathtub, right? If you have the stopper in, the water comes in, but it doesn't go out, right? It's just, you know, you come in and in and in until the bathtub fills up. So you have a rate of flow into the bathtub. When we think about these models, we have pull the stopper up so that the water also is leaving the bathtub, right? So sometimes if you are an epidemiology student or a biology student, I find it helpful to flip these so that it goes down like this, so that you can think about the inflow and the outflow, right? Because you're going to have a term that's coming in and you're going to have a term that is going out. And so leaving, right? So we have the negative here that tells us that this is the rate at which something is leaving this susceptible compartment. Leaving the compartment is this beta term, which is our transmission. And so that means if it's leaving, if this is the rate at which stuff leaves the susceptible compartment, it's entering into the infected compartment. And so this has a positive. So it's the same thing, right? It's coming out of here, it's coming into here. And then we have, because the eye has an arrow coming in, but it also has an arrow coming out, we also have the outflow from the infected compartment. And then the DRDT is going to be the inflow from the infected compartment into the recovered compartment. Now we could also add things like mortality, right? We might say, well, for this pathogen, some individuals who are infected are going to die as a result of their infection, right? So if we were going to add in this mortality, where would we put it up there? Obviously, it goes with the DIDT because it's a transition out of the eye compartment. What's it going to be? How do I add it in there? Is it an inflow or an outflow? Outflow. So we're just going to tag it on here, right? So basically, anytime we have a transition coming in or out of the compartment, we're going to kind of add it in here with a positive if it's an inflow, a negative if it's an outflow. So I can take that very simple set of equations and I can just simulate over time, and with an R0 of 3, it gives us this little epidemic curve, right? So this is basically plotting each of those compartments over time. We start with 1,000 susceptibles and 1 infected, and you can see that over time, the susceptibles go down, the infecteds go up, and we generate this epidemic, and we can see that over time, the recovereds go up, right? Because as people transition out of the infected state, they become recovered. And because we don't have individuals coming back into the susceptible compartment, we just have this single epidemic curve. So you could then take the same model, for instance, and we could add, vaccination. So who can tell me, like, we're making a simplifying assumption here about vaccination in this model. Who wants to explain to me what's happening with vaccination in this model? Yep. Exactly. So we're not adding a new compartment in this example, right? We're not adding a vaccinated compartment. We're going to keep it a little bit simpler and just say, we're just going to vaccinate susceptible individuals and we're going to allow them to bypass the infected compartment so that they never become infected. We're going to just dump them into the recovered compartment because those individuals are immune, right? So we're going to include vaccination in our model in this kind of simple way. And so then we would have 2 transitions out of the S compartment, right? So we would have this, but we would also have the vaccination rate coming out of the susceptible compartment. And if we use the same numbers and have a reproductive number of 3, we see that we get a very different, I wouldn't even probably really call that an outbreak, right? You get some cases, you start with 500. So if we vaccinate 500 individuals and we start with 500 susceptibles, basically, or 499 susceptibles, you can see that the susceptibles go down, we get a little bit of infection, but that vaccination or moving people to that recovered and immune category changes very significantly what you see in the dynamics of the system, right? So in your slide deck, you also have a couple of examples similarly written out this way, top to bottom, which sometimes I find a little bit more intuitive if you're not used to looking at them. And so you can see these, and this just gives you some examples of how to set these up. They're in your deck, so you can kind of look through them. And so keeping on time, because being overtime on the first day is never good. So hopefully, you've got kind of a primer of infectious disease epidemiology and kind of the different pieces you need to think about when you start putting together your simple models. And we're going to come back to those when we do kind of our simple model problem set right before lunch. It's going to give you some practice on your computer, working through some of these examples, setting up equations and getting them to run in R. All right. On that note, I will turn it over to Amy.
Yeah, thanks so much for being on time, and thanks for a great lecture, Amy. So
I just wanted to quickly mention that, this is a professional event, and the event organizer